For our next proof, we are going to be investigating secant squared of x minus tangent squared x. Now in the last proof, we had a plus sign here with sine squared plus cosine squared. Now we're going to have a minus, and you're going to see why there has to be a minus there. You're going to see why the plus just will not work. For the first step, we're going to break down the secant squared into secant times secant, since that's exactly what it means to square something. And we're going to do the same thing for tangent squared. Tangent squared is the same as tangent times tangent. For the next part of our proof, we're going to use the simple trig definitions. Secant is nothing more than hypotenuse over adjacent. So every secant will be replaced with hypotenuse over adjacent. Tangent is opposite over adjacent, so every tangent is going to be replaced with its definition of opposite over adjacent. So right now we have h over a times h over a minus o over a times o over a. This is what we started with, this is what we have now, which is equal to the same thing. We will now note that h times h is h squared and a times a is a squared. So we will then substitute those as such. That is the entire expression, sorry. And then over here we have o over a times o over a is just going to be o squared divided by a squared. So now we have this expression. This can be converted into one fraction. Why? Because they both have an a squared in the bottom. So now we will just have one denominator of a squared. We will fuse the numerators together, and now it will become h squared minus o squared, all divided by the common denominator of a squared. And now I want you to focus your attention to this right triangle that we've been looking at. We know we have a right triangle we're dealing with since we're talking about these trig ratios. So here's our angle. Let's say this is our angle x, and we have the adjacent side here, the opposite side, and the hypotenuse. Of course, this is a right triangle, so I'm going to put my little symbol there. Just like from the last proof, we know that the two side lengths, the two legs squared or added up are equal to the hypotenuse squared. Therefore, for this triangle, we can say that a squared plus o squared is equal to h squared. Now, if that's the case, watch what happens if we subtract o squared from both sides. We will get a squared is equal to h squared minus o squared. Now if we draw our arrow back to where we have here with this fraction, we have an h squared minus o squared right there. So we can substitute this with a squared, since we just showed that using the Pythagorean theorem of this right triangle. So for the next part of our step, I'm going to use red and just be consistent. The h squared minus o squared can be substituted with a squared, since that's what it's equal to here according to the Pythagorean theorem. And notice we already have an a squared on the bottom of this fraction, so it's just going to carry down, and now we have a squared over a squared, and we all know that that's just equal to 1. Anything divided by itself is 1. Let's take a look at what we started with. We started with secant squared x minus tangent squared x, and we've just proven using the Pythagorean theorem that secant squared x minus tangent squared x is equal to 1, and that will complete our proof. So therefore I'm going to write that out, and we will be done. Secant squared of x, or theta, again it doesn't matter, minus tangent squared of x is equal to 1. And again, don't forget that there is a minus sign here, and we needed that in order to make this proof work. There is no plus. Plus doesn't equal 1. You can see why that wouldn't work. If you go back through and look at our proof, you would end up with h squared plus o squared, which doesn't equal 1. Doesn't equal a squared. Right? In order for it to work, we have to use the Pythagorean theorem correctly. So that's it for this example. Secant squared x minus tangent squared of x is equal to 1. If you have any other questions about this, let me know.